Hi everyone. Welcome back to Dave's Math channel. I haven't made any videos in a while on calculus, so I figured I'd resume with my series on first year calculus, in particular my sub-series on integration. This is my 10th video in my sub-series on integration, and today I'm going to talk about a third very important method for integration, namely integration by partial fractions. So anyway, let's begin. So when do we want to use integration by partial fractions? We want to use it when the integrand is a rational function, a complicated rational function. And the idea is we start with a complicated rational function. And the first thing we do is we factor the denominator. Usually the denominator will factor into linear factors. Sometimes you get a quadratic factor. It's always going to be linear and quadratic factors if you're factoring over the real numbers, by the way. And there's like 5 different kind of forms shown here for what you might get. And then depending on the form of the rational function, once the denominator is factored, you get different types of partial fractions. The simplest case is where the denominator is the product of two linear terms. They say x minus a times x minus b, and the numerator has the form px plus q. It won't have any terms higher order than x. If it does, you can do polynomial division to get rid of them. But anyway, what you're left with when you do the partial fraction is you get something in the form capital A over x minus a plus capital B over x minus b, where now capital A and capital B are constants. They're unknown constants. And we can solve for them by, just solving the equation. Left side equals right side. And to solve that equation, you just multiply everything by the least common denominator, which in this case is x minus a times x minus b. And, when you're done, you equate like terms, constant terms, linear terms. And when you're done with that, you're going to get a system of linear equations for your unknowns. And they all work like this. So you'll see it'll be easier to see when I do some examples. And these can get pretty complicated. So I think today I'm just gonna do the first two of these forms. In a future video, I'll do the other ones. But anyway, let's just do some examples. Here's a simple example. Suppose we have the indefinite integral I equals dx over 1 minus x squared. So in this case, we're integrating the rational function 1 over 1 minus x squared. And the first thing we want to do is factor the denominator. And, it's pretty easy to see that 1 minus x squared can be written as 1 minus x times 1 plus x. So we can write the whole fraction as 1 over 1 minus x times 1 plus x, which has a partial fraction expansion of form capital A over 1 minus x plus capital B over 1 plus x, where now capital A and capital B are unknown constants. And now we can solve for capital A and capital B by just multiplying everything by the common denominator, which in this case is 1 minus x times 1 plus x. And when you do that, you're left with 1 on the left side, and you're left with capital A times 1 plus x plus capital B times 1 minus x. And then you just multiply everything out and collect like terms. And you get A plus B, plus that's a constant term, plus A minus B times x. That's a linear term. Well, now you'll notice that we just equate like terms. So a plus b, that's the constant term, and the constant term on the left was 1. So we get a plus b equals 1, and then a minus b, that's the coefficient in front of the linear term, a minus b times x. And since there's no linear term on the left, a minus b has to be 0. So this is the simultaneous equations we get. A plus b equals 1 and a minus b equals 0. This is a very simple system to solve. I mean, from the second equation, we see that b equals a. And then we just plug that into the first equation. We get 2a equals 1, so a equals 1/2. But since b is equal to a, that means b is also 1/2. So both a and b are equal to 1/2. And when we're done simplifying the 1 over 1 minus x squared, we find this partial fraction expansion is 1/2 times the quantity 1 over 1 plus 1 minus x plus 1 over 1 plus x. So that's how we do that. That's how we find the partial fraction. We're not done because we still have to integrate. But now it's pretty easy. We start with the integral we started with, I equals dx over 1 minus x squared. We already found the partial fraction, so now we just plug that in the integral, and we get 1/2. We can split this into two integrals. We get the integral dx over 1 minus x plus the integral dx over 1 plus x. And these are both very easy integrals to solve. If you like, you can solve them by substitution. And it's pretty easy to see that I'm not going to work out all the steps, but it's pretty easy to see that the first integral, dx over 1 minus x, is just minus ln of absolute value of 1 minus x plus c for some integration constant c. And it's also easy to see that the second one, the integral of dx over 1 plus x, is just plus the natural logarithm of absolute value of 1 plus x plus c. That should be a 1 plus x in there. So when we plug everything in, what we get is the integral is equal to the fraction ln of absolute value 1 plus x minus ln of absolute value 1 minus x all over 2 plus c. We can simplify this a little bit using properties of the natural logarithm. We can write the whole thing as 1/2 ln of absolute value of 1 plus x over 1 minus x plus some integration constant c. So that's how you solve that. That one's pretty simple. But let's do a harder one. So this one is going to be of the second form. Notice that the denominator, so here we have the integral of 3x plus 4 over the quantity x plus 2 quantity squared dx. And this is of the second form. You can see that the denominator has a square in it. So it's the partial fraction is going to look like this, capital A over x minus little a plus capital B over x minus little a quantity squared. So it's going to have that form, and let's just do it. So I went a little too far here. So so when we do that, we get in this case the thing in the denominator was x plus 2 quantity squared. So we're going to get capital A over x plus 2 plus capital B over x plus 2 quantity squared. So that's going to be our partial fraction expansion. And we find capital A and capital B the same way as we did in the last example. We multiply everything by the common denominator, which in this case is x plus 2 quantity squared. So when we do that, we get 3x plus 4 on the left, and that's equal to capital A times x plus 2 plus capital B. And again, we collect like terms, and we get capital A times x plus 2 times capital A plus capital B. So the linear term now, or the constant term, is 2a plus b, and that has to equal 0 because or no, 4. Is that right? Yeah, 2a plus b is 4. That's the second equation. And the linear term gives us, we just have a for the coefficient for the linear term on the right, and then on the left it's equal to 3. So we have a equals 3. So that's our system. A equals 3 and 2a plus b equals 4. Yeah, that's easy to solve. We already know a, so we plug it in the second equation. We get 6 plus b equals 4. That means b equals minus 2. So when we're done, we get I equals 3 times the integral dx over x plus 2 plus, or minus 2 times the integral dx over x plus 2 quantity squared. Once again, these integrals are very easy to solve. The first one just gives you a natural logarithm. We get 3 times the natural logarithm of absolute value of x plus 2. And the second integral is just going to be 1 over x plus 2. So you get, or minus 1 over x plus 2. So the second integral is going to give you plus 2 over x plus 2. And you always have an integration constant when you're done. So that's the answer. That's how you do that one. Not too much harder than the first one. Anyway, that's all I'm going to do today on partial fractions. I'll do some more in the next video. Anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.